Good evening, everyone, and welcome to the Orange Coast College Planetarium. My name is Jerome Fang. I'm chair of the astronomy department here, and I asked Jessica if I could give the introduction tonight because I have a story to tell about your speaker tonight, Evangela Shread, coming to us from Caltech. Evangela is going to say more about this, but she started here at OCC over 4 years ago, and she was in my intro astronomy class, and this was when we were all on Zoom. And she came and talked to me on Zoom, along with another of her fellow students, Trevor, and they wanted to do a research project in astronomy. And I said, yes, that's awesome, let's do it. And so they started on a project involving galaxies, and over the next few years, actually, they worked on it. They presented it here at our campus symposium that year. Then they went on and took it on the road, as you should, and presented it at other places and conferences and venues. And just a few weeks ago, officially, the research paper that they wrote actually got published, and so we're super excited that they did that. So I'm very, very proud of Evangela. Evangela will say more about where she's been since she left OCC, but I'm really excited to hear her talk. I hope you are too. She'll be talking to us about her work she's doing currently, the low-mass galaxy frontier, from simulations to surveys. So a big warm welcome to Evangela.
Thank you very much, Jerome, for that warm introduction. Yeah, I'm just really honored and pleased to be here tonight as your Skylark speaker. Yeah, as Jerome told you, I first was a student at OCC over 4 years ago, and I'm going to be talking a little bit tonight about my journey from being an Orange Coast College student to being a graduate student at Caltech. And I'm also going to talk to you about the cool science that I do. Before we dive in, I just want us all to look at the background photo here. If you've seen maybe photos of the brain, like maybe it looks like little nodes and then you have filamentary structures going between them. Well, this is actually a simulated image of the cosmic web. This was made with a computer simulation. It's, terabytes of data, years of work, and some of the work that I do involves bridging these types of simulations with the galaxies that we observe around us. Yeah, so I'm just going to walk you through what we're going to talk about today. So of course, we're going to hear about my journey. And my science part of this talk falls into 4 areas roughly. I'm going to give you an introduction to what dwarf galaxies are, so hopefully you can come out of this with an appreciation for them. We're going to talk about how many we have found and how many we think are still out there but have not been discovered. And we're going to talk about this role of computer simulations and how we can connect those to what we see with telescopes. And finally, we're going to talk about what some of these upcoming and future telescopes are. I'm going to talk about my involvement too in one particular mission that is planned and that I'm very excited to be a part of. There we go. Yeah, so I guess first off, just by a show of hands, how many of you are OCC students or alumni? Wow. Okay, there's a lot of you here. That's great. So then maybe you understand then what it's like to be a non-traditional student, and that's been my experience. I first went to college out of high school in 2016, and things didn't really go as planned. I left after about 3 semesters, and I tended to some personal matters. And I had always had this love of astronomy and physics, even from the time I was in high school. I had the opportunity to do research at a local lab while I was in high school, And so when the pandemic rolled around, I realized that this passion had never left me. And I was ready to go back to school. Well, I lived like right down the road here in Costa Mesa at that point, and it was suggested to me by actually someone who's a very good friend of mine now that I enroll at Orange Coast College, and one thing led to another. As Jerome mentioned, I reached out to him, and so I wanted to get involved in research again. And the research I had done in high school was more about planets and planetary science. I didn't really have any appreciation for, or I didn't know much about galaxies at all, actually. But in 2022, we presented a project about the connection between hydrogen gas in large galaxies and how massive their central regions are. And we presented this at the OCC Research Symposium. And this was a really great experience. Pictured here, you'll see Jerome and also Trevor, and then another OCC alumni, Cameron Law, who got his bachelor's from UC Irvine in physics and astronomy. And I don't think any of us were expecting it, but we won like the first place poster prize that year. And it was like a really reassuring experience for kind of all this hard work that we put in. And we decided to take this a step further. So the 240th meeting of the American Astronomical Society was that summer, and for those of you who don't know, the American Astronomical Society meetings are kind of like the largest American conferences we have for astronomy, and it's a really great opportunity for up-and-coming researchers to present their posters, and that's what we did. And actually, we entered a student research competition and got an honorable mention for our poster here at AAS 240. I think it was largely because of Trevor's presentation skills. He's an excellent public speaker. And, but yeah, as Jerome mentioned, we recently published a paper on this work in the Astrophysical Journal. And, I share this because if you keep asking questions and just if you keep being persistent, you can really do a lot in research. Research is all about resilience and persistence. And, doing this project is what led me to developing this interest in dwarf galaxies. So I'm just very happy to have been a part of this research team here at Orange Coast College. So after Orange Coast College, having some technical difficulties, I transferred to UC Berkeley to finish my undergrad. And, for the current OCC students, you might be wondering, what is that transition like? And, I can say that it's not easy to transfer to a UC from community college, but I was incredibly fortunate to, I chose Berkeley, which actually has some pretty amazing resources for transfer students. Like, I felt immediately a part of a community of transfer students, and I was able to become accustomed to a different academic environment within a semester, I think. I had the opportunity to do some other research there with the Space Sciences Lab. I was involved in an up-and-coming X-ray, or gamma ray telescope called the Confidence Spectrometer and Imager, where I worked on a student project to essentially optimize the infrastructure that that telescope will be using to process the data and the images it collects. And believe it or not, that actually led me directly to my lab, or my research group that I'm in now. which has a focus on both galaxies and actually high energy astrophysics, like what this specific telescope is involved in. So I also had the opportunity to do some cool summer research, and I say this because for current students, being able to do these types of 10-week or maybe 8 to 12-week internships is really great for testing if you want to go to grad school and if you want to make research a career. I got to hold space rocks, which was awesome, at the Johns Hopkins Applied Physics Lab, working on characterizing meteorites, creating, almost like simulating the conditions required for meteor formation in a lab. And from that experience, I had the chance to contribute to a couple different projects, which was really reassuring for my desire to make a career out of doing physics research. So I graduated in spring 2024, and applying to grad school was a bit of a formidable process. But now that I'm on the other side of it, I do feel motivated to help current undergraduate students through this process. And I actually got involved in an outreach program at Caltech to essentially pairs current graduate students with current undergraduate students. And so I had the opportunity to meet with the student weekly and give advice on the application process and help her through her essays. And that was just very rewarding, because a lot of us coming from these non-traditional backgrounds don't really, I didn't have a parent who had gotten a PhD, so now I am in my second year, and I just think that through this kind of non-linear process, to use a physics term, I've become more resilient, and I just encourage the students in the audience to keep persisting, and I also remind you that once again, things like resilience and persistence are what makes a good researcher, in my opinion. So if you have questions about this part of the talk, feel free to ask at the end, but we will go into what I'm doing now and why dwarf galaxies are so exciting. So first, we should ask, what are dwarf galaxies? They are low mass, faint, usually spread out. On this image here is a satellite of our galaxy. A satellite meaning, most galaxies in our universe live in groups with a central that is usually pretty massive, like our Milky Way, and then there's a bunch of galaxies orbiting it, and we call these satellites. So looking at this, it really looks like a blob of stars. Maybe you've seen images of beautiful spiral galaxies where they have the arms and a dense central core. Well, most dwarf galaxies don't look anything like that, and for this reason, they're incredibly hard to detect. Sometimes they get confused for star clusters, and how we're able to distinguish them from star clusters is actually by the fact that they have a lot of dark matter. Now, dark matter is the invisible matter component of our universe. It comprises about 3/4 of the matter in our universe, and we don't know much about its particle nature, but we can observe its effects. And dwarf galaxies in particular are important for helping us discern the properties of this invisible matter. so dwarf galaxies are not a monolithic population. Some live in isolation, meaning they're far from massive groups. Here's one example. There's a lot of galaxies that are in the background. Those are more distant, but it's kind of living on its own. And still some live in clusters, more massive groups. Here's an example of a region of the Virgo cluster, which is 16 megaparsecs away, which roughly translates to 50 million light years, give or take. So that sounds far away, but that's actually pretty close by if we're talking on cosmological scales. I'll try to give you more of a sense for what that is later on in this talk. And one other thing I want to highlight about this image is it was taken with the Rubin Observatory, which has a new survey, which has the acronym LSST, and the Legacy Survey of Space and Time. It's going to have its first data release in the coming year, and it is expected to revolutionize the study of dwarf galaxies in the local universe. And we will be talking more about that. So, they also have different star formation properties. Some are blue, and as a result, they tend to appear brighter than galaxies that are not star-forming at the same mass. And some have stopped forming their stars, so they appear better. And that's because stars that are young and new tend to emit a lot more ultraviolet radiation, which is on the bluer end of the light spectrum. And it turns out that looking at whether dwarf galaxies are still forming stars or not can tell us a lot about how galaxies evolve from the beginning of the universe to today. And on that topic of cosmic history, I want to put dwarf galaxies in a cosmological context for you. So cosmology, which is this word I've been throwing out a lot in this talk, is essentially the study of the history of the universe from the Big Bang, some 13.5 to almost 14 billion years ago to now. And the first galaxies started forming about 12.5 billion years ago. And we can actually probe some of the earliest galaxies formed now with the James Webb Space Telescope, which maybe you're familiar with. And why that is interesting is because a lot of the faintest dwarf galaxies in the local universe actually have imprints of the early universe within their stellar populations. So this epoch of reionization, which I put in red here, shows you visually that era in cosmology that we're interested in. And essentially we think that some really small galaxies stopped forming their stars around that time, but they still exist today. And these might comprise some of the red and quenched low mass galaxies that we see. Quenched meaning they've stopped forming stars. So dwarf galaxies are natural laboratories for more than just looking at imprints of reionization in the early universe. They're important for studying star formation and stellar feedback. Stellar feedback is the process by which stars die and the gas and matter and energy they eject starts to influence the matter between galaxies, actually, and within the galaxy. So it's important at a galactic scale. These are also probes of dark matter physics. In some dark matter theories, the mass of the dark matter particle is bounded by the size of low mass galaxies. People explore alternative gravity theories too. Now, we think that our current understanding of gravity probably might not need to be modified, but just to kind of throw it out there that people are looking to dwarf galaxies for all sorts of theoretical physics applications. And lastly, dwarf galaxies are also the subject of challenges to our current best model of cosmology. One of them I'm going to highlight because it is kind of relevant to the rest of this talk is the missing satellites problem, which is essentially describes the tension between simulations of the dark matter halos that galaxies live in and observations of satellite galaxies. So I will unpack that a little bit. So we know and believe that all galaxies essentially live in a halo of dark matter, which is, you can think of it like we need this clump of dark matter essentially to exist before it can attract the gas and precursors of stellar matter. And, it is within these halos actually that galaxies form. And so some 15, 20 years ago, some theorists ran a simulation that only modeled the dark matter halos, and they found that around dark matter halos that would correspond to a halo containing a galaxy the mass of our Milky Way, there were a lot of these low mass halos orbiting it. And so this made astronomers wonder, where are the missing satellites, right? There should be 1,000 around the Milky Way. And it turns out actually that over in the years since, if you include your actual stellar matter and gas matter, it turns out that a lot of these halos actually can't host a galaxy. So the missing satellites problem is more or less considered a resolved problem. But there is still some discussion that is actually relevant to what I'll be talking to you about whether other massive galaxies nearby that aren't the Milky Way have a missing satellites problem. Yeah, and so more about the different types. We talk a lot about their brightness or their mass, because in this case, or in astronomy often, the brightness of an object is correlated with its mass. The ones on the top row here are our more massive dwarf galaxies. There's the Large Magellanica Cloud, which is also on the ceiling there. So you saw that when you were walking in. That is a more massive dwarf galaxy satellite of the Milky Way. So these ones we think we can see out to pretty far distances. And however, the galaxies that are further down on this chart are less massive and much harder for us to see. So these are all located, it turns out, within a region we call the local group, which I'll show you a bit more in a bit. But the sort of next frontier of dwarf galaxy studies is really trying to find more of these ultra low mass galaxies at greater distances, because these are the types of galaxies that are going to help us understand the early universe and dark matter and how stars form in the kinds of environments that exist within dwarf galaxies but don't necessarily exist to the same extent in more massive galaxies. Yes, so this region, the local group, It's about 3 million light years away from us. That's what we consider the boundary. And it turns out that most of what we know actually about dwarf galaxies comes from looking at this little region of space. And, you know, the nice thing about it is these are spatially resolved, which, if you're an observer, means you can do a lot more by looking at the image. I mean, a lot of times astronomers will look at galaxies far away, and it's essentially like a point source, which means you can't really learn that much about it just from, you know, a few pixels in your image. Yeah, so here's just a diagram, if you will, of the local group. It basically has the Milky Way and its satellites, and Andromeda and its satellites. Andromeda being, of course, our next door neighbor. We're kind of in a pair group, if you will, with Andromeda. And I'll talk a bit more about this too, but in a sense, the Milky Way and Andromeda kind of have a special place in the universe. Yeah, so most of what we know about these low mass systems comes from the local group, and which really is, so if the Earth is the size of the universe, then the local group is probably your immediate next door neighbors. Like, it's a very small part of the universe, even if 3 billion light years sounds like a lot. And, you know, recently there has been some great observational efforts to find and resolve low mass galaxies within the local volume, which is a slightly bigger region that might be like our, you know, kind of part of a town, if you will, in our analogy here, which has been great for advancing our understanding of dwarf galaxies, but we still think that we're missing a lot of them. And that future telescope should hopefully help us find many more of these. And on the right here is just a depiction of part of the local volume. So you can see there's many other galaxy groups. The Milky Way and Andromeda and 31 are at the center, but there's a lot of other galaxy groups that are kind of like our own. And this begs the question, okay, beyond the local group, how many dwarf galaxies are there? We know that, or we believe that these galaxies are the most common in the universe, but it seems like these are perhaps the least understood. So, in answering this question, perhaps we need to set some ground rules, because we just can't expect to detect every low mass galaxy in the local universe. Part of that problem is the ones that are super diffuse, that just look like a blob of stars, are hard to distinguish in a crowded field. They might be outshined by more massive galaxies, especially in very cluttered environments. So perhaps if we focus on the more massive class of dwarf galaxies, then we can make inferences about the dwarf galaxies that are farther away. So, how many are there in the local universe? I wanted to show this plot because I think it shows an important point about our theoretical limitations, actually, in trying to answer this question. So I'll kind of walk you through what this plot is doing. So on the y-axis, going up, we have the increasing cumulative number within 100 megaparsecs, which is about 320, I think, million light years. And on the x-axis, we have the mass of the galaxy. So on the right-hand side, that's kind of considered like the most massive low-mass galaxies that we have. And then we have, at this end, we're kind of bounding it at 10 to the 6 solar masses, which is basically just the lower limit for this classical and bright dwarf galaxy population that we're interested in, because we think we can probably detect a lot of these now. So in a cumulative number plot, the more steep the line is, like the more things you have around that point, and as things get flatter, you have fewer total objects in that region of the plot. So what this is telling us, essentially, ignoring like absolute numbers, is that empirical models, right, like models that come from observations of galaxies, which are the ones that are colored, blue, green, and pink, those don't agree below about a third of the way over from the right. They start kind of deviating. They also have large error bars. So that's what we know kind of observationally. Like these are sort of 3 state-of-the-art models for the number of galaxies in the local universe. Now, the gray region of the plot, that dotted black line, comes from more theoretical models. These combine the simulations of dark matter halos that I mentioned previously, and combine them with also what we know. They're also somewhat informed by empirical models of the number of galaxies, but they are largely considered a theoretical result. But the point of this plot is that none of these agree at the lowest masses. And, you know, so can we do better than that? I mean, is there, you know, how can we answer this question of how many galaxies are there in the local universe? And part of what is striking, though, about this plot is we only, within 100 megaparsecs, which I chose this distance because this is kind of an important scale on a cosmological sense. At about 100 megaparsecs, usually the universe starts to look the same everywhere, give or take, in the sense that, you know, if you have sort of like a fabric and it has a pattern on it, and if you zoom out enough, like, it starts to look kind of the same. And so we only know of roughly like 20,000 dwarf galaxies within 100 megaparsecs, but all these models tell us there should be at least 100,000. I mean, you know, even much more than that, like 1 million. So this tells us that at least 95% of the local low-mass galaxy population has yet to be discovered. And, you know, I'll also mention that a lot of these models are extrapolated at lower masses from models of higher mass galaxies too, which is how we're able to come up with these predictions in the first place. Whoops. We went one too far. There we go. So yeah, just to kind of summarize, the problem in answering this question of how many dwarf galaxies are there is that empirical and theoretical models don't actually seem to agree that well. And, you know, so can we do better? And I spent roughly the last year trying to see if we can do better, and so the goal here is we're going to use some cosmological simulations of galaxies. These are special in the sense that they model both the dark matter halos, but also the physics that leads to galaxy formation. So it models stars and gas and all of the rich physics that we know is important for the formation and evolution of galaxies. So, okay, here's a fun exercise. One of these galaxies is simulated, and one is an actual real observed galaxy. So, does anyone, okay, so by a show of hands, do you think the one on the right is the simulated galaxy? Okay, some of you? Yeah. How about the one on the right? Do you think that one is? Okay. So it seems like most of us think the one on the right is the simulated one. So, it turns out actually, this one is observed, and this one is simulated, which, I know, I mean, I did this to fool you, because I want you to appreciate how intricate these simulations are. I mean, the one, I will say, the one on the left, it was, this group took this simulation and they imposed certain, like they tried to make it look like a Hubble image. Like they took like the exact filters of the telescope and did some kind of post-processing, if you will, to make it look like an observed galaxy. But this is just a beautiful Hubble image too. I mean, it looks like perfection. So, we're gonna do a harder one next. So, okay, before I ask you, I'll just explain what this is. So this is sort of a map of the cosmic web or structure traced by galaxies out to a pretty big distance. So our universe is at kind of, or not our universe, our galaxy is at the vertex in each diagram. And this is as if we are looking out, but we are also, this is also kind of made into a 2D image. So, but yes, we are looking out into the universe. So, okay, who thinks the one on the left is simulated? Okay, some of you. And how about the one on the right? Okay, let's see how we did. This one's pretty, yeah, okay, so I think more of you got that the one on the right was simulated. Very good. But, so, you know, the point of this, again, is, you know, cosmological simulations have gotten to a point where they're really good at mimicking the observable universe. And similar to the last example that we looked at, what was done here was they imposed sort of the same observational limitations that we have on the left here, but they mimicked that in the simulation to make it look like it would have been observed. Okay, so let's see, hopefully we have a video. Uh-oh. Yeah. Oh, that's okay. I can describe it. But we had a nice video that essentially, it's a really powerful thing, and I encourage you to go and look this up after. It's from the Illustrious TNG collaboration. They have this whole website with videos and pictures, and it's incredible to watch because essentially what it shows is this distribution of gas and stars and dark matter, like, you know, just evolving over, we're almost there, evolving over billions of years, but over the span of like a minute and a half. It's incredible. So what these simulations do is they track the evolution of these different components of galaxies over cosmic time. So they do rely on our best both observational and theoretical understanding of galaxy formation and evolution from the, you know, like the first few hundred years of the universe to now. So what we're doing is like we take these equations of gravity and fluid dynamics actually, and we evolve them in various time steps, and there's a lot of very intricate physics that gets coded in these simulations. And perhaps like the most incredible thing about these simulations is that they're able to model realistic processes, like how, again, how stars form and die, how black holes, because most massive galaxies have a supermassive black hole at their center. These will accrete, they will suck in gas, if you will, from the surrounding galaxy, and then when they reach a certain mass, they will start ejecting some of that mass and matter and energy back into either the galaxy around it or into the region between galaxies. And this is a very important process, actually, for the making star formation stop in massive galaxies. And I will say that these simulations are actually necessary for modeling galaxy formation and evolution in a statistical way. This is something I'm very excited about, and because I'm a physicist at heart, and we can only get so far on pencil and paper, and then at some point, because these equations are stochastic, which means we know sort of the rules that govern them, but the results themselves are, they're chaotic. They're very, the tiniest shift in your initial condition can just cause completely unpredictable results. Yeah, and there's a lot going on here, so don't worry too much about what these are saying, but this is just to show you that the complexity of the physics that go into these models. And these are informed by how we think galaxies form and evolve. And this is really important because actually modeling galaxy physics on a computer is very computationally complex. There is a reason why for many years, a lot of times simulations only focused on the dark matter because it's just easier to model than it is to include all these different effects that lead to the formation and evolution of the stellar components of galaxies and their gas content as well. So the simulation that I have spent a lot of time looking at is from the Illustrious TNG collaboration, and this one particular run called TNG 50, because the Illustrious TNG simulations are a suite of simulations. This kind of bridges the gap between two classes of simulation. Now, there's also a lot happening on this plot here, but essentially what this is modeling is sort of the computational difficulty of simulating galaxies. So on the y-axis, we have the increasing resolution, and the x-axis is essentially how many galaxies we can simulate at once, which is the same as how large of a volume we can probe. And because these simulations take years to write and run, we've long been limited by either volume or resolution. And TNG 50 is nice because it kind of bridges the gap between these two types, right? We have a pretty large volume, but also pretty good resolution, which is important, it turns out, for our ability to study dwarf galaxies. We need a high resolution, but we also need a large enough volume to get a large enough sample to analyze. And here's just an amazing photo of the thousands of real analog galaxies that exist within the TNG 50 simulation. So yes, these are all simulated galaxies. And frankly, to me, they look indistinguishable from real ones. It would make a nice blanket, I agree. Yeah, so, just kind of with some of my time remaining, I'll try to walk you through a little bit of how do we make the simulated universe like the real one? Well, the first step is let's identify some pairs of galaxies in the simulation that are like the Milky Way and Andromeda. And this is because, as I alluded to earlier, we think that the Milky Way and Andromeda actually have kind of a special place in the universe. I mean, there are certainly other groups of galaxies that kind of are like our own, but our kind of best understanding tells us that if we have a pair of galaxies like Andromeda and the Milky Way, the surrounding environments are likely to be roughly the same across different analogs of these pairs and simulations. So essentially there's a connection between having two galaxies like Andromeda and the Milky Way and the surrounding sort of larger scale galaxy environments within some 30 million light years. And the next step is, now that we've identified our Milky Way analog, we're going to transform the positions and the speeds, the velocities of all the galaxies in our volume relative to this analog. We're essentially going to make it look like we're actually observing from the Milky Way. And then kind of the last step is we want to impose real observational effects. So if you go into the desert and you look at the night sky, you'll see the Milky Way. And while it's beautiful to look at from Earth, it's kind of a problem for observers because it means there's a whole plane of the sky where distant galaxies become obscured in visible light. So in order to have a true like-for-like comparison between simulations and observations, we need to account for this, and we need to remove this plane from our simulated environments. And this is the result. On the left here, we have observed low-mass galaxies between in this classical and bright dwarf galaxy regime. And then on the right, we have classical and bright dwarf galaxies from the simulation. And this is all within a volume akin to the local volume, which is this special region out to 30 million light years. And as you can see, so I'll say that we don't expect them to look exactly the same because, as I mentioned, galaxy evolution and formation is a process we can only understand statistically. So there will be some differences in terms of the actual structure, but if you look at the sort of number and maybe the kinds of structures you get, you can see that they have similarities. And then if we go out to 25 megaparsecs, this is the largest volume that the TNG simulation allows us to study at this resolution, you start really seeing some more differences. There's a lot more galaxies over here than there are there. And this is where we're really getting into the heart of the problem. Like, we're definitely, compared to this simulation, we're definitely missing some low-mass galaxies. And to kind of quantify it a bit, we can go to the next slide where we have an actual plot. And this is, again, a cumulative distribution. The red here are the observed galaxies, and the blue are the simulated galaxies. The left within is the first slide that I showed out to 10 megaparsecs, or the local volume. And this was what we just saw here on the right. So, so as you can see, it becomes pretty flat in the red line there, it becomes pretty flat on the right side. So that's really telling us that compared to the simulated line, which continues to shoot up, we're definitely missing some low mass things, especially on this half of the plot, which is the lower mass part of the plot. And what this tells us is, overall, we're missing, there's about 3.5 times more simulated galaxies in that image than, and within the TNG simulation, than are in these cataloged observations. And I will say that these observations represent a huge, comprehensive sample drawn from all of the best and largest surveys that we have as an astronomy community. So this is really an interesting result. I mean, this is telling us that we're missing more, within this distance, we're missing 3/4 of the dwarf galaxies in this mass range. So there's a small caveat, which is that the total matter in this TNG simulation is actually a bit bigger than what we expect within the Milky Way, which could mean that this is actually an upper bound on the true number of dwarf galaxies that we should expect to see within this volume. Even so, we can start to make some predictions for what this undiscovered population of low-mass galaxies should look like. And I won't get into the specifics here because for the purposes of this talk, I think it's enough to talk about the properties of these. But essentially, we think that a lot of these missing galaxies are isolated, meaning they're far from nearby massive groups, and many of them we think are actually no longer forming stars, or at least are not forming stars right now. And this is interesting because a lot of what we know about the evolution of dwarf galaxies assumes that most isolated galaxies are still forming stars, actually. And this is because a lot of times dwarf galaxies, especially the ones that are satellites and more massive ones, they stop forming stars because they interact with other more massive galaxies, and this will quite literally strip them of, starve them of the gas that they need to form stars, or maybe strip them of that gas. And so it's interesting that the simulation actually says that some galaxies that are in isolation, pretty far from these more massive galaxies, might actually have stopped forming stars. And this kind of aligns with other recent studies that there might be this hidden population of isolated and red galaxies. Oops. One too many. But the good news is that, if there are a good amount of these galaxies, then the next generation of large sky surveys will be able to detect them, we think. And I'm going to go through what a wide, deep, and systematic survey can do through an example. Yeah, so I mentioned at the beginning of this talk Vera Rubin Observatory's Legacy Survey of Space and Time. And that is because this is going to, astronomers really believe that this is, this represents sort of a new era for dwarf galaxy studies and for many other astronomy studies. And that is because, simply put, this telescope is really quite incredible. It's going to cover a wide swath of sky, so about 44% of the sky, so almost the entire southern hemisphere. And it's going to be deep, which means that it's going to be able to look at really faint objects, compared to the Sloan Digital Sky Survey, which was a very major flagship observatory for imaging the visible part of the spectrum of galaxies. It's going to be able to probe even deeper, 2 to 5 times deeper, if you will. And it's going to be a systematic survey. It's going to image the entire southern sky over the course of 10 years, visiting spots various times. And the reason that's important for finding these low mass, isolated, and red galaxies is a lot of times observationally, astronomers will look at a major galaxy, a pretty large galaxy, and they will search in the region around it for low mass galaxies. And this kind of makes sense because we expect there to be a lot of low mass galaxies that are satellites and more massive ones. And so as a result, there's maybe a slight bias in current searches for low mass galaxies, but by having a systematic survey, we can search all regions of the sky, including ones where there aren't any nearby massive galaxies. Yeah, and just with my preliminary analysis, I estimate that LSST could find as many as 5,000 or 6,000 new dwarf galaxies within about 80 million light years, within 25 megaparsecs. As I mentioned previously, this is perhaps an upper bound on the true number. Maybe it's more like 1,000 to 2,000, but still, LSST really represents the next frontier for dwarf galaxy studies. And lastly, I'm going to talk about the Ultraviolet Explorer, or UVEX. This is a collaboration that I'm working on as a second-year PhD student. So this is going to, for the name, this images in the ultraviolet. And unlike LSST, which was in the visible part of the light spectrum, ultraviolet is also important because it's good for tracing recent star formation, and it turns out that sometimes, observationally, low mass but nearby galaxies can look like higher mass distant ones. So this telescope in particular will be good for distinguishing these galaxies from one another and allowing us to study both what's nearby and what's further away. So the other nice thing about this telescope is we're in this era of what we call multi-messenger astrophysics, where we have observatories and telescopes that can image all parts of the electromagnetic spectrum. And all parts of the electromagnetic spectrum tell us something different about galaxies. So the James Webb Space Telescope, for example, in the infrared, is able to tell us about galaxies that are very far away. And a lot of the low mass galaxies that are being imaged by JWST, we can find analogs for those in the local universe. And so UVEX here will be able to essentially study these analogs for the more distant galaxies of JWST. And this is, again, very exciting for bridging the gap between these local laboratories, if you will, for galaxy evolution and, like the first galaxies formed that we can now see. And also, just as part of this collaboration, I'm working on kind of coding the infrastructure for simulating images and spectra that we should hopefully be able to see with this telescope, which will be launched post 2030 or later. So it's still very much in development, but it's a very cool effort. And if you're curious to learn more, uvex.caltech.edu has some information about the types of science that will be possible and about the specifications of the telescope itself. So, in summary, what have we done? We've talked about what low-mass galaxies are, and I showed you that these are missing from our current observations. Computer simulations, like TNG, can help us connect the theories we have about galaxy formation and evolution and the actual galaxies we see with our telescopes. And I think that the most promising discovery space for these low-mass galaxies might be for isolated low-mass galaxies that have stopped forming their stars. So red and dead, or maybe they'll start forming stars again. It's hard to say, but presently, not forming many stars. And finally, future telescopes and surveys are equipped to revolutionize galaxy studies, but especially for low-mass galaxy studies. I mean, we're truly in an era of low-mass galaxy discovery, and within the coming year, LSST should be releasing its first data release, and so expect to see lots of pretty pictures and hopefully some new dwarf galaxies that maybe we didn't know about. So with that, thank you for having me here tonight, and I'm happy to take questions. In the back?
Evangela, this is about your educational journey.
Sure.
Way back at West Coast College, before you transferred to Berkeley, did you take advantage of the honors program?
You know, that's a good question, because I actually didn't. I actually didn't. And, you know, looking back on it, I kind of wish I had. I remember I had a math professor who had encouraged me to take one of the honors classes, and I think the reason I didn't was because I had a work conflict or something. But yeah. Yes? Oh yes. So yeah, so with coding, so I will kind of just all on my computer, I will code in a couple different languages. If you're familiar with Python, a lot of astronomers code in Python. I also code C and C++, and just also have to do some command line manipulation, with kind of bash scripting, and if those terms are familiar to anyone. I do lots of a lot of the work I do is on a computer essentially. So, yeah. Anyone else have a? Oh, right there. Yeah.
Thank you for your excellent talk. Would you say applications like TMAS help you with astronomical surveys for identifying dwarf galaxies?
TMAS, the survey, or? Oh yeah, no, that's a good one actually.
Could you repeat the question?
Oh sure, it was if certain surveys, the TMAS survey, right, have also helped me in my research. I guess what other types of surveys or resources have I used? Actually TMAS has come up, and only briefly, because looking for a good sample of observed galaxies, I came across like all sorts of databases like Hyperlita, of course some digital sky survey, something called like the local volume galaxy database. There's NED, I forget maybe what that stands for, but that is, it's affiliated with Caltech, it's another database. But yes, and also things like the 2-mass survey. And, luckily for me, there have been so many great observational efforts to essentially streamline all these different resources. So quite literally for me, I guess I didn't even put a citation to that paper, but it was by a group at Utah that kind of put together a bunch of these different surveys, and all I had to do was just take the data and analyze it. So yeah, but all of these things are super accessible. Ingrid?
When you come up with a better way of statistically accounting for numbers of dwarf galaxies, their masses, their distances, and relations to major galaxies, how is this going to influence our thinking of the evolution of our universe?
Oh, that's a very good question.
Yeah.
Yeah.
Now you've got some more data.
That's true.
And maybe in a way, you can kind of test that data against something local, like your local group. So,
Yeah.
Gee, this is close. We've got the technology to go in and really kind of nail this down with our local group.
Mm-hmm.
And we know this data to be true.
Yeah. How
does this influence it?
Yeah.
Versus your big, your much larger statistical model. Like
Yeah.
So there's a lot of complexities that are involved.
Yeah. No, I mean that's a really good point, because something that I did not really get into in this talk is that this is a test of the simulations themselves. Like they have very good predictive power, but like for instance, the galaxy stellar mass function is in TNG 50 is calibrated at, or essentially the stellar mass function that they use to calibrate sort of the like sub-grid resolution models in the simulation are essentially stop at a stellar mass of about 10 to the 8 solar masses, so much more massive than these 10 to the 6 galaxies we're looking at. And so so in a sense, like this statistical model is itself something that remains to be tested by the observations that we should get at greater distances. And like you also make a really good point too about how most of what we know comes from the local group. And hopefully this kind of next wave of observations will be able to tell us more about low mass galaxies at greater distances, and really inform just our understanding of like small scale challenges to the lambda CDM paradigm of cosmology. So hopefully that somewhat answered your question. Mm-hmm. Maybe like one more question. I don't know how much time we have, but I thought I saw a hand somewhere. Okay. Yeah. Oh, up front. Oh, AI. That's a very good question. Well, I will say actually, the project that I did as an undergrad with a confidence spectrometer and imager, like a huge goal of that project was to actually use machine learning to optimize the kind of data infrastructure for that telescope. So there's like a huge space now for AI and machine learning in astronomy, and I mean, it definitely is kind of here to stay. So, yeah, I mean, there's all sorts of discourse about that, and you know, I'm kind of just coming into this space, so I'm, you know, there's certainly a lot of more opinions out there, but. Yeah, I mean, I think so. You know, I mean, it's certainly like, you know, how I view it is like it's a tool. You know, it's a tool for us to be able to gain deeper insights in the science. And I mean, you know, can AI do, you know, quantum field theory? No. Like, can it do, you know, can it do very complicated physics? Like, you know, not with human input, or not without human input, if you will. So it's kind of, you know, I mean, who knows, maybe it will get there, but for now it is like kind of just a very beneficial tool. All right, well, I think that's probably it, because I know there's like a stargazing part, so